We recently learned dynamic programming, and matrix exponentiation caught my attention. We're probably all familiar with the Fibonacci problem and a few ways of solving it. Dynamic programming lets us solve the problem by using bottom-up with the time complexity of O of n and the space complexity of O of 1. However, there is an even more optimal way of solving the problem using matrix exponentiation with the time complexity of O of log n. I spent the past 2 days studying the algorithm and the solution, and I want to talk about what I learned in my own interpretation. I want to mention that I did not solve the problem myself. I studied an existing solution, and I put the credit in the link down below. To understand matrix exponentiation, we need to first understand exponentiation by squaring. Let's take a look at some examples. So here we have x to the power of 8. Traditionally, we would just solve the problem by multiplying the number 8 times. But that's not a really efficient way of doing that. By using exponentiation by squaring, we can actually cut down the time by more than half. This is how we execute it. So we multiply the number by itself, which gave us x to the power 2. We then multiply x to the power 2 by itself, which gave us x to the power 4. Then we do that again, which finally gave us x to the power 8. So instead of the 8 steps from a previous approach, this approach only takes 3 steps. So it's worth mentioning that it's a lot easier to get to powers of 2. So what about odd exponents? We need to take into consideration both even and odd exponents. There is actually an easier way to do that. We can use binary. Let's say we have 15 as our exponent. 15 in binary representation is 1, 1, 1, 1. That gives us 8 plus 4 plus 2 plus 1. And because we all know that x to the power of a plus b equals to x to the power 8 times x to the power b. So x to the power 15 equals to x to the power 8 times x to the power 4 times x to the power 2 times x to the power 1. And notice these numbers are really the numbers here. So these are the steps that'll take for us to get to x to the power 15. Let's take a look at the function implementation of this method. So here we have a function that takes in a base number and an exponent. We're using recursion here. So we have a base case where n equals to 1. For every recursive call, we're dividing the exponent by 2, rounding the number to the nearest integer by using math.floor until it reaches the base case. So if the exponent is an odd number, we multiply the return value from the recursive function by the base number itself. So the call stack looks like this. Let's say we have an exponent of 15. We're dividing 15 by 2 for each recursive call because it's an odd exponent, it's an odd number. We're also multiplying by the base number. So we're dividing 15 by 2 until it reaches 1, in which case we return the base number x to the power of 8. And we multiply the base number for each recursive call. That gave us this. Notice it looks exactly like what we had in our mathematical solution. So let me run the function and show you what I mean. I'm calling the function on the number 2 to the power 15. It takes about 4 steps to get to this large number. which is really good. We're not considering 2 because it's the base number. So now let's take a look at the Fibonacci problem. So for the Fibonacci problem, we have an initial setup like this. We want to calculate the next number in sequence by adding the previous 2 numbers. So really, we only really need the previous 2 numbers to calculate the next number in sequence. What we can do is we can store these 2 previous numbers in a vector. And then we want to calculate the next number in sequence, store that number in the new vector along with the previous number. The way we're doing it is by using matrix. So we all know that the fib of n is the sum of the previous 2 numbers, which in this case are the 2 elements from the previous vector. What we can do is we can represent this equation in a different way. So fib of n, we can write it out as 1 times fib of n minus 1 plus 1 times fib of n minus 2. So that give us fib of n. Same thing, and this is the first element in the new vector. For the second element, we can do the same thing. We can represent the equation this way by multiplying fib of n minus 1 by 1 plus 0 times fib of n minus 2. So really this element, the second element of the new vector, is also the sum of the 2 elements from the previous vector. But because we already have this as the first element, we're multiplying the second element by 0 to cancel it out. So our 2 by 2 matrix looks like this. We're taking the constants from these equations and put them in the array. So we're following this formula. We're initiating a vector that stores the 2 previous numbers we use to calculate the next number in sequence. We multiply the initial vector by the matrix, which is this, that gave us the new vector. And we take the first element of the new vector, and that'll be our final solution. So let's take a look at the function implementation again. If you look at this function here, and the function in the Fibonacci solution, they look almost identical. But instead of using a base number, we're using a matrix. So we're calculating the matrix to the power of n. And we created a helper function that calculate the multiplication of matrices. Because multiplying matrices is a lot more involved than multiplying numbers. We basically have to multiply each element of the matrix by the rest of the elements exactly once. So then we use the helper function in the main function right here, just like what we did in our initial function for the multiplication. If the exponent is an odd number, we're calling the multiplication again because we're multiplying the return value from the recursive function by the matrix itself. That gave us the final matrix. And finally, we're calling the helper function one more time, and we multiply the final matrix that we get from the main function by the initial vector. And that gave us the final vector. So in the helper function, we also specify a condition because the matrix we have has a length of 4. but the vector has a length of 2. So when we're multiplying the final matrix by the initial vector, it will actually hit this condition and give us the final vector. Notice that when I call the main function, I'm using n minus 1 instead of n. Let me show you why. If we're initiating a vector to fib of 1 and fib of 0, and we're using this formula to calculate the new vector by multiplying the vector by the matrix. Notice the relationship between this number and this number. So really, if we want to get to fib of n as the first element of the final vector, this number really is n minus 1. So 3 is 4 minus 1, 2 is 3 minus 1. So in order to get to the final vector, we're calculating the matrix to the power of n minus 1. Then we multiply that by the initial vector, which is this one. I know it's very convoluted, but it actually makes a lot of sense. This is why we need to use n minus 1 as our second argument for our main function. So let's take a look by running the function. By comment this back out. So we want to get to fib of 8. Let me comment this back out. Run this. So it takes about 4 steps to get to the number 21 if we want to calculate fib of 8. Comparing this with the bottom-up solution, we run this, it does take all these steps to get to the final number 21. Let's try a different number. Let's try a bigger number, 15. We run this. The matrix exponentiation approach takes about 5 steps to get to the final number 610. And if we're using bottom-up approach and we want to get to fib of 15, and notice it takes a lot more steps to get to the number 610. So really, matrix exponentiation is a very powerful algorithm to calculate large numbers. As you can imagine, when an application scales quickly, this algorithm with big O of log n will actually beat all the other algorithms because of its efficiency. I hope this video has given a clear overview of the matrix exponentiation algorithm and its advantage of real application. Thank you.